Welcome to quantum error correction class. I'm Daniel Gottesman. This class is going to be taught by myself and Benny Yoshida, who's sitting in the back. We're both faculty here at Perimeter, which is why we're making you come all the way over here. Let's see. So the other benefit of having it at Perimeter is that the lectures will be recorded and on Perimeter's webpage. I will try to put links to those recordings on the class webpage here, as well as the problem sets when they're coming up. So the textbook that I've handed out to you is, as if you go through it a little bit, you'll notice it's very much a work in progress. There's some sections that are unfinished, and there's not too many figures and stuff like that. So I would ask that you don't distribute it beyond students in the class. It's because in this case, I didn't work on it since the last time I have class, but there's various versions that have been produced over the years, and I don't want kind of these half-finished versions floating around too much. But if you do happen to be using it and you have any comments, errors, stuff that's not clear, anything like that, please do let me know, because it is still being worked on. So let's see. So the class is, for those who are taking it for credit, it's going to be, the grading is going to be based 70% on the problem sets, which tentatively we decided to be one short one per week. So I handed out the first one already, due next Thursday. And then the remaining 30% will be a final project, which is going to be a paper that you write based on reading a couple of research papers related to the topic of the class, and then giving a presentation probably for the last lecture will be student presentations. So just to get an idea, how many of you are currently registered for the class? So 1, 2, 3, 4, 5, 6, 7. And how many are thinking of registering but have not done that yet? OK. OK. And I'm fine with the people who didn't raise your hands either of those times. You're welcome to continue to come. Yeah, so that covers kind of the basics. The web page has a bit more detail about the topics we'll be covering. But that's a little bit subject to change as we kind of work out how it's gonna go. And so the plan right now is for me to teach the first half of the class, and then Benny will teach the second half. So are there, yeah?
Is there an audit requirement, like if we choose to audit?
Well, I don't really care about that. To the extent if you're welcome to come to the class regardless. I mean, I guess University of Waterloo, if you want to have it on your transcript as an audited class, then you have to fill out some paperwork. But that's fine.
But the problem set and everything.
I think if you're auditing, there's no real need to do that. You should try to attend the classes, but it's OK. So we need 2 more copies. Do you have?
I do have one.
You have one already. It hasn't changed actually from last time. So. OK. So any other questions about the logistics of the class? OK. So then let's get started on the scientific content, which would be an overview of what we're going to do here. So quantum error correction, obviously the goal is to correct errors in quantum systems. So the basic idea is we're going to take some number of qubits and encode them using extra qubits. And based on the hopefully well-chosen encoding, we'll be able to identify errors that might have occurred on a small number of qubits and fix them. So that's basically, when it boils down to it, a kind of a communication scenario. So we have Alice over here, and Bob over here. And Alice is wants to send some qubits to Bob, but there's some noise in the channel between them. Okay? And so the assumption here is that Alice and Bob both have perfect quantum computers. Okay? And so the encoding is whatever encoding they decide on. And they both know what that encoding is supposed to be. And then any changes to the encoding, any way it differs from that, is going to be due to the errors. But then, so that's kind of the error correction scenario. I guess I should say that this doesn't have to be kind of literal communication. It could be that Alice is in the past and Bob is the future. And so then it's just a matter of storage of quantum information over some amount of time. And again, in that case, we're assuming that errors are occurring at a low enough rate that it's only the errors in the intermediate time when it's being stored that matter, and not in the encoding and the decoding. But then we get to the scenario of fault tolerance. So if we're actually building a quantum computer, that assumption that errors are very low is not that great, right? And so whenever we do a quantum gate, there's going to be some possibility of an error associated with that, either just because of decoherence and the time it takes to do that gate, or because our control procedures that we're doing are not perfect. And so they will have errors as well. And so basically the first month of the class is going to be about error correction, aspects of error correction. And then the second month, roughly, is going to be about fault tolerance. And in fault tolerance, we're trying to deal with the fact that the gates that we do are also not perfect, which means that when we say, oh, we're going to encode the data in this quantum error correcting code, well, the code that we create won't be exactly the code we intended to create. There'll be some chance that it's wrong. And so we have to be able to deal with that as well. And also the error correction procedures we do will not be perfect. And moreover, it's not just enough to say we want the qubits to go from Alice to Bob. We also want to modify the encoded qubits in order to do a computation, right? If we want to run Shor's algorithm, for instance, well, there's a whole bunch of gates that we have to do, and they have to be right. If you do the wrong gate, then you won't get the right answer. Even if it's just one gate somewhere in the middle, that could give you a totally wrong answer, potentially. So we need, in fault tolerance, to not just have a way of dealing with errors in the encoding and decoding, but also to do fault-tolerant gates, to do gates that are robust against errors occurring on single qubits. And kind of the kind of culminating result of the theory of fault tolerance is the threshold theorem. And the threshold theorem says that if you can get the error rate below some threshold value, which is some sort of constant of nature, then it's possible to use these fault-tolerant ideas to make the logical error rate arbitrarily small. And therefore, you can do arbitrarily long quantum computations reliably. Okay? And of course, doing this requires extra gates, extra qubits. In the standard threshold theorem, both of those blow up by a factor that's polynomial in the logarithm of the length of the computation you want to do. So that's kind of reasonable asymptotic scaling, although in practice, the numbers are pretty big. And so the threshold theorem is important because it tells us that, in principle, there's no kind of fundamental barrier to building a big quantum computer. And that's, kind of today we're at this exciting threshold where the number of qubits that people can make is starting to explode, and the error rates are down low enough that we're kind of at least in the vicinity of this threshold. And what that's saying is that if they can just kind of keep on this trajectory, then software will kick in to make the quantum computers that they build reliable enough to compute whatever we want within the usual limits of quantum computation. Okay, and so that's roughly the second month. And then the third month will be kind of miscellaneous topics, but I think particularly topological codes, which have emerged as kind of one of the leading candidates for fault tolerance in real-life quantum computers, but also have a lot of relevance to condensed matter physics and maybe even some other things as well. I don't know if Benny's going to talk about some of those other things, but we'll see how things go. OK. So that's kind of an outline of the class. But what I wanted to do start at today is just kind of the very basics. So what kind of errors are we talking about? What is a quantum error correcting code? And kind of what the basic properties of quantum error correcting codes are. So errors. So in that picture I drew up there with the wiggly line, what does it mean? What am I talking about when I say those errors? So remember, again, this first month is error correction. So we're basically, you can think of that communication scenario and assume that Alice and Bob have perfect encoding and decoding operations. It's only the errors in the middle that we worry about. So the kind of most general thing that can happen in that circumstance is, in a quantum system, is a completely positive trace-preserving map. And so what it is a map of a density matrix to some other density matrix. And it has to satisfy three properties, although one of them is kind of redundant. So the first one is that it should be positive. So positivity says that if rho is positive semi-definite, then S of rho is positive semi-definite. Okay? So this is a clearly very sensible condition, because if rho is a density matrix, it's positive semi-definite, and we want the image to also be a density matrix. So it also has to be positive semi-definite. Right? Otherwise, you get things like negative probabilities. And that wouldn't make sense. And so the second condition is that this is actually not strong enough to ensure that you always get a density matrix. What you need is something called complete positivity. And so complete positivity says, well, OK, this is fine if you're just putting in this state rho that's uncorrelated with anything else outside. But what if you have an entangled state and you put part of the entangled state through this quantum channel? This is also called the quantum channel or quantum operation. Well, that could also, the output could also be a density matrix globally, right? Suppose you have some state sigma such that trace over some reference system of sigma is equal to rho. Okay, then and sigma is basically a quantum state, so sigma is also positive semi-definite. Then it should follow that for this map S, that if you apply I tensor S to sigma, then the result is positive semi-definite. Okay? So this is what I just said, that if you take an entangled state, then apply the channel to part of it, then the resulting output state is also a density matrix. Okay? And so this completely positive is the CP in CPTP. Okay? And then the third condition gives you the TP, which is that it's trace preserving. And so trace preserving is another kind of very sensible condition, right? It says that the trace of S of rho is equal to the trace of rho. And in particular, when rho is a density matrix, its trace is 1. It says that the probabilities of the various different outcomes, if you make a measurement, add up to 1. Then the trace of rho also supposed to, sorry, the S of rho is also supposed to be a density matrix, so it should also have trace 1. Okay? So these are three very sensible conditions. And it turns out that, well, what I've said so far should be enough to convince you that they're necessary conditions for a valid quantum operation. But it also turns out that they're sufficient conditions. So if you have any map that satisfies these three conditions, it can actually be realized in principle in a quantum system. And there's a property called purification, which is that any such map can be realized by using some ancilla, which we might as well start as 0, and doing some unitary, and then throwing away some qubits. It doesn't have to be the same number or the same dimension in Hilbert space as you used as the ancilla. And then this input would be rho, and this output would be S of rho. Okay? So any map that satisfies these conditions can be realized in this way, with U unitary here. So the other useful way of writing these completely positive trace-preserving maps is called the Krauss representation. And so any CP-TP map can be written in the following way, as the sum over K of AK rho AK dagger with sum of AK dagger AK is equal to the identity. So you can think of this as saying that this quantum operation has different possible things that can happen. And those are the AKs are the different things that can happen. And you kind of choose one of them at random, although actually the probability of each thing can depend on the state. And then apply the AK to the state. Okay? So the catch here is that the AKs don't have to be unitary. Okay? And, well, that's one of the catches. Another catch is that this representation is not unique. So there can be multiple different Krauss representations for the same quantum operation. Okay? So let's look at some examples. So the first example is probably the easiest one. It's really a class of examples. So if we have a unitary map, so then S of rho is equal to U rho U dagger. Okay, so that's this Krauss representation just has one term then. So there's of course lots of different U's that you could come up, but here's some examples that will be showing up later today. So we have X. This is the Pauli sigma X. So this is a bit flip. And you see it takes 0 to 1 and 1 to 0. Right? So you can think of this as kind of basically a classical bit flip error. Although, of course, it can act on superpositions as well. And then you have the phase flip, which is the Pauli sigma Z. And so that's taking 0 to 0 and 1 to minus 1. And then it's also useful to consider the third Pauli, which is Y, equal to I x times Z, which has this matrix. Well, yeah, so that takes 0 to I1 and 1 to minus I0. Okay, but of course, there's infinitely many more unitaries you can consider. So one I'll be using later in the lecture is this phase rotation, r theta, which I want to write e to the minus I theta 0, 0, e to the I theta. Okay? So that's a simple set of examples, and I introduced it mostly just to write down these definitions, because they'll be important later. Okay, so, but then there's channels that do something more interesting, that involve more than one Krauss operator. So one kind of common channel, both in theory and in real life, is the dephasing channel. So the dephasing channel has two Krauss operators, and with probability 1 minus p, nothing happens. You just get back rho. And with probability p, you get a phase flip. So, of course, this Krauss form normally has z rho z dagger. But if you look at this, z is equal to z dagger. So I'm not going to bother. So when p is equal to 0, this is just the identity map. Nothing happens. And as p gets larger, you're more and more likely to have a phase error. And it turns out that p equals a half, it's not p equals 1, but p equals a half is kind of the maximal error. Because if you go all the way to p equals 1, then you never have rho, and you still have z rho z. So of course that's wrong, but it's wrong in a very easy, predictable way. It's then just back to here. It's back to a unitary map. Whereas if you're in the middle, then you're actually losing coherence. You have the potential of making pure states into mixed states. And in particular, if you have any superposition at p equals a half, then it's destroyed. So at p equals a half, if you start with the state that's alpha 0 plus beta 1, then the density matrix that comes out is alpha squared 0, 0 plus beta squared 1, 1, which is just a classical mixture with the appropriate probabilities between 0 and 1. Okay? So the p equals 1/2 totally destroys any superpositions. So it kind of makes it a purely classical probability distribution instead. Okay. So, I mean, another way that we like to talk about the dephasing channel is on the Bloch sphere. Probably a lot of this is familiar to people, but I just want to review it in case it's not to everybody. So the Bloch sphere, is this representation of a single qubit. So 0 is up at top, well, or 1. Let's call it 1 up at top and 0 down at the bottom. And then you kind of have x, y, z axes corresponding to these polys in a certain sense. And then any density matrix, so any pure state is on the surface of this sphere, and a density matrix is inside the sphere. I don't really want to go into the details if you haven't seen it, but the upshot is that the dephasing channel will shrink it. Well, so anything in this z-axis is going to stay the same, right? Because that's a mixture of 0 and 1. And so it stays the same. And anything else is going to kind of shrink towards that. So what happens is you get some ellipsoid inside. This sphere shrinks to an ellipsoid while preserving that z-axis. Okay? And in the case of the fully dephasing channel, p equals a half, it shrinks everything down actually to the axis itself. Okay, so another example of a CP-TP map is that you'll see come up quite a lot is the polarizing channel. So this polarizing channel is very common in theoretical work, but not as common in actual experiment. And the reason theorists like it is because it's the most symmetric channel you can have on a qubit. So in particular, what it does is it takes rho to, well, with some probability, you get rho back. And then with equal probability, you get x, y, or z applied to the state. Okay. So again, when p equals 0, this is just the identity. But as p gets larger, you get kind of more and more errors. And the thing is, they can be in any direction. So unlike the dephasing map, which was shrinking to an axis, this takes the Bloch sphere and shrinks it uniformly. So you're shrinking a sphere to a sphere. What's not so obvious, I mean, when you look at this, it's just, you can see that it's treating the x, y, and z axes the same. But what's not so obvious is that it's actually treating any direction the same. And one way to see that is that there's an alternative. So remember I said these Krauss representations are not unique. So you can find a different Krauss representation for this same map that's more manifestly symmetric. And so here's one. So in this representation, you say with probability 1 minus 4/3 p, you leave the state alone. So you notice that this probability is actually different. With probability 4/3 p, you take the state, throw it out completely, and replace it with a maximally mixed state, okay, which is the center of the Bloch sphere. Okay, so that tells you why this is shrinking, right? Because you're taking whatever state you started with and mixing it with the maximally mixed state. And so the reason that these probabilities are not the same is because in this case, there's some chance. I mean, the maximally mixed state has some component that's the original state you started with. Okay, so you replace it with something random, but randomly it might just be the same. Okay, and that's what makes these two things actually match. Right. Okay. So are there any questions on this so far? Yeah.
So with the dephasing channel, if instead of the cross breakdown being with z's, it was x's or y's, would it do the same thing with the Bloch sphere just along a different axis?
You mean if you just had the same thing but with p x rho x?
Yeah. Would it just shrink?
Yeah. So it's just one poly. Yeah, that's right. So it would shrink along whichever axis. Yeah, because so if it's x, it's shrinking to the x-axis because that commutes with the x, whereas the other axes don't commute, so they kind of get knocked out. And so that brings up the kind of obvious generalization of these two things, which is a general Pauli channel. Which we can write this way. So now we're going to have a different probability of error of x, y, and z errors. So with 1 minus px minus py minus pz, we do nothing. And then with probability px, we do x. And py, we do y. And pz, we do z. And what this does to the Bloch sphere is it also shrinks it along each axis, but by a different amount, potentially. So again, you're getting an ellipsoid at the end. Okay. So one property of all these channels that I've shown you so far is that they're mixtures of unitaries. And that's not really doing justice to the full power of these CP maps. I guess another property that they have is all the ones I've shown you are unital, meaning that they map the maximally mixed state to the maximally mixed state. But again, that's not the most general thing that can happen. And so the last channel I want to show, example channel, is called the amplitude damping channel. And so this is, again, one that shows up a lot in real life, in a lot of physical systems. And so what this does is it involves two cross operators. And this is what they are. So this is actually a family of channels. And so what this does to the Bloch sphere is it shrinks it, but it shrinks it down. Instead of shrinking it into the middle, it shrinks it down. And you can kind of see that that 0 is the, if you kind of, so gamma is a parameter that says how strong this amplitude damping is. And if you put up gamma all the way to 1, then you see that A0 will project on the 0 state. And A1 will take 1 and push it down to 0. So in the limit of gamma going to 1, you're shrinking this down to the point at the south pole. But if gamma is not 1, then you're only partially doing that. And so these two things are, so this one represents, if you think of, so one place that this shows up is relaxation of an excited state. So for instance, if you have a 2-level atom, the ground and excited state, so 1 should be the excited state, 0 is the ground, and then 1 will sometimes spontaneously emit, say, a photon, and relax back down to the ground state. And that's what happens when A1, or that's what A1 represents. You see the 1 is going to a 0. But when that doesn't happen, something still interesting happens to the state. So remember, the Krauss representation had to satisfy this condition, that sum of AK dagger AK is the identity. And if you were to take A0 to be proportional to the identity, you could never get that to work. Because A1 dagger A1 is going to be basically proportional to 1, 1. It only affects 1, right? It can never affect 0. And so this 1, 1 term has to be smaller than 1. Smaller than the 0, 0 term in particular. And what that represents physically is, well, suppose you don't see a relaxation from the excited to the ground state. Well, if it was in the ground state to start with, that's not surprising at all, right? It couldn't relax. But if it was in the excited state, then there was some probability of having it relax. And so the upshot is that if you start with a superposition of ground and excited, and you don't see a relaxation, that means that it's more likely it was actually in the ground state to start with. And so you take that superposition, you kind of shift some of the amplitude down to the ground state, even though you haven't seen the jump. And so that's what this Krauss operator is representing. And so here you see that it's really much more interesting, right? Because neither of these is a unitary. They're not something that you could say, oh, I want to do this. That's not an option. You can only do this when in conjunction with something else non-unitary that could also happen with a certain probability. Or similarly, you might say, oh, I want to take 1 and map it down to 0. But you can't reliably do that by itself. You have to combine it with this other Krauss operator or some other set of things. OK? Yeah?
So can we think of, like, in a sense, the amplitude damping channel, when you said superposition of 0 and 1, the ground state and excited state, it's the sense that we know since the qubit goes through this channel,
right?
If it's still relaxed, If it's still in the relaxed state, then we know there's a higher chance it wasn't the relaxed state to begin with. Like knowing information.
Sorry. So suppose you have this atom here, and you're monitoring it to see if it emits a photon. If you see a photon, well, then you know it must have gone from the excited state to the ground state, and that it must now be in the ground state. But if you don't see a photon, that's telling you that it is more likely it was in the ground state to begin with. So if it was just a classical probability distribution, then that kind of inference would be maybe a little bit surprising, but not really confusing. In the quantum case, it's just actually a superposition that's getting rebalanced, not just a probability distribution. So it's some kind of quantum Bayesian update, you can think of it, if you really want to think about it that way. But it's not, it doesn't matter if you're actually looking to see if that photon came out or not. That's the other aspect of it, right? That if it comes out but you don't see it, it's still the case that the superposition changes. Because, someone else out there might see it. Well, okay, still the case, modulo interpretations of quantum mechanics. Really beyond the scope of the course. Okay? Any other questions on these example channels? Okay, so then I guess, okay. So the last thing I want to say, so this is all examples of channels for single qubit. Now, to do error correction, we're going to have to deal with multiple qubits. In particular, we're going to have to at least consider the possibility of multiple qubit errors. But I want to distinguish between an error. If you have a multiple qubit system, I want to distinguish between an error that's really only affecting one of those qubits and one that's affecting many of them. So let's have a definition. So suppose we have some tensor product operator. And these don't have to be unitaries. They can just be any linear maps. So then we say the weight of M is the number of non-identity tensor factors. Okay, so if you have, I tensor x, tensor x, tensor I, that's weight 2. And so the weight is sometimes written as WT, so the weight of M. Okay, and so then if I have a completely positive map, I want to define how many qubits it acts on kind of non-trivially by taking advantage of this weight. And what I'm going to do is I'm going to look at the Krauss operators. So I'm going to say so if we have a completely positive trace-preserving map on n qubits, that can be written with Krauss operators such that each of the Krauss operators is a sum of operators with weight less than t. So this is going to be called a t-qubit error. Okay? So the idea here is that this weight thing is only defined for tensor products. But if you have a sum, if you have an arbitrary operator, you can write it as a sum of tensor products. And if you can write that sum so that it's a, say, a sum of things of weight 1, then it's really only acting, in some sense, on 1 qubit at a time. I mean, it's really acting on many qubits, because it could be a superposition of something that's weight 1 on the first qubit and something that's weight 1 on the second qubit and something that's weight 1 on the third qubit. But it's still kind of less general case than something that acts on many qubits in a more complicated way. And for the purpose of error correction, it turns out this is the right way to think about it. So then if we have each of the Krauss operators is in this way a sum of things that acts on only a few qubits at a time, then all the possibilities for what can happen with the CPT map are, in the same sense, acting on only a few qubits at a time. And what we're going to do is we're going to come up with quantum error correcting codes that are designed to correct t-qubit errors. So this is why it's important to think about this sort of thing. The sense is that this is like a small error, right? If you have many, many qubits and t is very small, then a t-qubit error, I mean, it could be large in the sense of changing states to orthogonal states, but it's small in the sense that it's only affecting a small fraction of the qubits. And that comes up a lot. So, for instance, suppose you have just a classical error process that, with some probability, independently for each bit, will flip that bit. Okay, some probability p. So well, then what's the probability of seeing errors on exactly t bits? Well, there's so prob of flips on. So there's n q's t sets of t bits that we could look at. And the probability of having errors on exactly that set of t bits is p to the t, and then 1 minus p to the n minus t. So this is the probability that we have errors on exactly the t chosen bits, and the probability that we have no error on the other n minus t bits. Okay? And of course, the probability of having bit flips on less than or equal to t bits is the sum of this thing up to t. Well, where this would be j, j going 0 to t. And so the point is that when p is small, a small independent per bit probability of error, then this thing is highly peaked at low values of t. And when n is large, implies that it's peaked at around t about equal to p times n. Right? That's a sensible thing. If you have many, many qubits, the number that you expect to have bit flips is about p times n. And in particular, the probability of seeing bit flip errors on many more than p times n bits is quite small. And so it's quite reasonable to say, oh, I'm going to just create an error correcting code. Well, maybe I'll choose t to be slightly larger than pn, but I'm going to have an error correcting code that corrects that many errors. And then I can just kind of neglect the probability that we're going to have more errors than that. And so this argument was for classical systems, but a very similar analysis holds in the quantum case. In fact, if you want to be careful about it, you can make the following statement. Suppose we have some channel that's close to the identity. And in particular, E minus the identity is less than epsilon. For some small epsilon. So this diamond norm is some particular measure for distance in the space of channels. If you don't know what it is, it doesn't matter too much. This is just a concrete statement of how close this channel is to the identity. So if this is true, then there exists some other channel, which is a T qubit error. E tilde, such that n copies of this original channel is close to E tilde. And there are some constants here. So in the book, I have a proof of this. Those constants are probably not the tightest or best ones. And it turns out when doing error correction, you don't actually need this theorem. You can prove something much better in the context of error correction. The difficulty is that this is saying E tilde has to be an actual quantum channel, which is stronger than you really need. But what this is supposed to do is to give you an idea that roughly this statement is also holding in the quantum case. That when you have independent noise, even when it's a general quantum channel, you can approximate it by some quantum channel that acts on only a few qubits at a time. Okay, when the channel is close to the identity. Okay? And so philosophically, this is again supposed to justify saying we're going to come up with quantum error correcting codes that will handle a small number of errors on only a few qubits, T qubit errors, and then neglect things that are larger than that. Yeah?
So is the statement that some CPDP map is a T qubit error independent of the Krauss representation? Because you define it in terms of...
Well, so the operative word here is can be written. So I haven't actually thought about this very heavily, but my expectation is that there will be examples where there might be one Krauss representation that involves many qubits and a different Krauss representation that involves fewer. And then you should use the one that involves the fewest.
Just take the minimum overall?
Yeah. Yeah, I mean, normally you're not even interested in taking the minimum and getting kind of the best value. You just want to say, well, T is what I know how to handle, so can I write it in terms of T? And if I can do even smaller, that's not that important. I mean, so the reality is that most of the time when we're dealing with quantum error correction, we don't have to go into the weeds of exactly what the channel is, for reasons that you'll see hopefully by the end of today. It's enough to kind of make a list of errors that we want to correct. And then we're going to correct those errors, and kind of any channel that's built out of those errors is going to come along for the ride. So a lot of this stuff is actually, at least this page here is you should think it is more motivation rather than something that's actually going to be in detail important for the course. Yeah.
So like in that theorem, like we're using the same E. Like we're taking a single.
So this theorem.
Yeah, this theorem here. There's a single E, but like in
yeah.
actual quantum channel, we're probably interested in like a mix and match of different types of errors. So there's like.
Okay. So it depends what you're asking. So in this particular, the way I've written it, we have n qubits, and each of them experiences the same channel E. You could generalize this, it'd just be kind of messy, to the case where this is E1, tensor E2, tensor E3, tensor E4, tensor E, et cetera. But they're all close to the identity. If that's what you're asking, then yes, it doesn't apply, but you can generalize it easily. The other thing you might be asking, which is also important to address, is that this channel kind of incorporates a wide variety of things that can happen. Okay, so think, for instance, of this polychannel. Right? You might say, well, I'm thinking about this channel, and there could be dephasing noise. Okay, sure. But there could also be some bit flips, and there could be both at once. Well, that can be written as a polychannel. Just one channel that's kind of taking into account everything that might happen to this qubit. Okay, so this E really does incorporate all the different possibilities, right? So if you might say, well, I actually don't know. Maybe it's a polychannel. Maybe it's an amplitude damping channel. And sometimes, with probably 2/3, it's a polychannel. With probably 1/3, it's an amplitude damping channel. Well, then you can still write that as another channel. You can say the actual channel is 2/3 times this plus 1/3 times this. Okay. Now, there's yet another case where you say, well, it's going to be one of those two things. I don't know which one, but it's always going to be that one, right? So either all the qubits experience the polychannel, or all the qubits experience an amplitude damping channel. So in that case, you can also write it as a channel. It's 2/3, but now it's 2/3 of this tensor n plus 1/3 of this tensor n. And so that is no longer this form, and this theorem doesn't apply.
So we have these channels that are each 1 qubit, and we're taking an n tensor of those.
Yeah.
Is there a reason why we haven't looked at channels that the Krauss decomposition is 2 poly operators tensor together, and then it'd be an n tensor of those together?
The reason is just I wanted to kind of keep it simple.
Oh.
There's no fundamental reason. You can absolutely deal with channels that act on 2 qubits or 3 qubits or whatever. So in the context of error correction, probably in a few weeks we'll talk about, most of the time we talk about qubit codes where it's kind of broken down into individual qubits, and so we care about counting individual qubits. But even then, we might care about correlated errors on those qubits. I will talk at least a little bit about codes for QDITs, where you have not just a 2-dimensional Hilbert space, but some larger Hilbert space. And in fact, the problem set uses bosonic modes, which are infinite dimensional. Again, these are just examples so that you could see what sorts of things we normally talk about, and partly to establish notation. So when I talk about X, Y, and Z, you know what I'm talking about. But kind of the fundamental philosophy here is going to be the same. When we break it up into QDITs of a given size, we care about how many of those QDITs have errors. And then the same thing applies. Yeah?
What's the intuition behind that the quantum channel should be close by empty?
Why are we demanding this?
Oh, well, what's the intuition?
Yeah. So this is a condition. And the reason I'm looking at that condition, that's kind of corresponding to saying this probability of error is small. Okay? So the context is that if we have a situation where errors are very common, we're probably not going to be able to do error correction then, because there's just too many things that can go wrong. We can't handle them. If errors are rare, then we probably can handle them. But there's kind of 2 ways in quantum mechanics that errors can be rare, right? So one of them is to say, oh, we have some polychannel, depolarizing channel, and P is very small. So most of the time, we're actually getting the right state, and then these other things are happening. But if you look at this amplitude damping channel, that doesn't really apply, right? When gamma is small, but non-zero, every time the state changes, right? Whether you have A0 or A1, the state is changing. Okay? But when you have A0, it's not changing very much when gamma is small. It's almost the same as what it was before. If you have A1, it does change a lot. But that's very rare when gamma is small, because this happens with probability that's like gamma squared, I think. Yeah. Okay? So this amplitude damping channel kind of illustrates these 2 things. You can either have a small probability of something big happening, or you can have a small amplitude of something happening. And so the state, another example of that is that R theta. When theta is small, again, something is always happening to the state, but it's still very close to what it started. Okay? And so that's this condition here kind of encapsulates both of these two different ways that the error can be small. And the theorem says that in the context of many qubits, that both of them boil down to something that's approximately saying only t qubits are actually having a significant change. OK. So any other questions on channels? Let me see here about pacing. Yeah, OK. So in that case, let's move on to actually talk about error correction. So first, let's talk about classical error correcting codes. So I'm not going to go into detail about classical error correcting codes. We'll talk some more about them next week. But let's talk about the simplest error correcting code you can imagine, which is the repetition code. So in the repetition code, we're just encoding a classical bit, so we just have to care about 0 and 1. We're going to encode 0 as 3 zeros and 1 as 3 ones. OK? And suppose, remember, we're in this communication scenario. Alice sends one of these two messages through the channel. And there could be probability p of error per bit. But as I discussed, we're just going to approximate that by saying, let's just consider the possibility of one error. So one bit gets flipped. And suppose we end up on Bob's side with something like 0, 1, 0. Well, Bob is going to say, oh, at most one bit got flipped. So this must have come from 0, 0, 0 and not from 1, 1, 1. And so then Bob will correct this back to 0, 0, 0. OK. So suppose we tried to use the same philosophy to make a quantum error correcting code. We would say, oh, OK, so we're going to do some quantum repetition code. And we're going to encode the state psi as 3 copies of psi. OK, so how is that a good idea? No, why not?
Can't copy psi for arbitrary psi?
Right. No cloning theorem says you just can't do this. I mean, it would be a great idea if you could do it, but you can't. It's not allowed, right? The no cloning theorem says no. So, I mean, actually, if you think about it, that's kind of a big problem for quantum error correcting codes, right? I mean, classical error correcting code, it seems like it's based on this notion of redundancy, right? If you're repeating the information in multiple places so that if one bit goes wrong, you still have copies of it. But if you can't make copies, it's just not allowed by physics, then how are you possibly going to be able to do a quantum error correcting code? So that seems like a fundamental problem that we're going to have to overcome. Obviously, we can overcome it, or I wouldn't have 11 more lectures in this class. But at the moment, it seems like a problem. And if you think about it, start to think about how classical error correction works, you can quickly come up with some other problems. So for instance, Bob might look at this thing and say, oh, the middle bit is different. Therefore, I should correct it back to 0, 0, 0. Right? There's 1, 1, and 2 zeros. So 0 must have been the right one. But you see the problem with that from a quantum case is it involves looking at the qubits, right, which is going to collapse superpositions. So that would be a problem as well. OK, and so even if we can deal with these first two problems, it's going to be, if you think about it, it's clear that quantum error correction is going to have to be more complicated than classical error correction. Because not only do we have to deal with things like this, bit flip errors, right? That's an X error. We also have to deal with phase errors, right? Those are going to be important. We have to need to preserve the phase of a quantum system as well. And I mean, really, it's not, it doesn't just end there, right? Because I gave you a whole bunch of examples, right? We have bit flip errors, we have phase errors. We also have these continuous rotation errors. So there's actually an infinite set of unitary errors. And then there's things like dephasing and amplitude damping and all sorts of stuff I didn't even write down. Okay, so there's really an enormous spectrum of errors that can occur on a quantum channel, compared to a classical bit where you just have 2 bits and you could switch them. That's all that can happen. Okay, so at this point, obviously, it looks pretty grim for error correction. But let's not try to handle all of this at once. Let's just kind of start out slowly. And let's think about this classical repetition code and try to make it work somehow in the quantum case. So we're going to forget about correcting phase errors, and we're going to correct about coherent rotation, stuff like that. We're just going to want to correct bit flip errors, right? We can do that classically. So why can't we also do it quantumly? Using, in fact, the same encoding. So let's do that. We're going to encode 0 as 3 zeros, and 1 as 3 ones. Okay? And so all I did was I put kets around the classical repetition code. And now it's a quantum code. Except this is only saying what happens on the basis states. Right? So what I should really do is also look at superpositions. But linearity tells me what I have to get when I do that. Right? If I have these basis states defined, then I know that alpha 0 plus beta 1 has to go to alpha times this plus beta times that. Okay? And immediately you can see that this is not violating the no-cloning theorem. Right? This is not equal to 3 copies of alpha 0 plus beta 1. Right? That would have things like alpha cubed and alpha squared beta and so on. Okay? So this is allowed and this is not. And so it's a good thing that this is the thing that we have. And in fact, you'll see that when alpha and beta are both non-zero, that the state we're getting out here is an entangled state. And so that's kind of how we're able to extend the classical bit flip repetition code to the quantum case by taking advantage of entanglement. Yeah, okay. And so that's kind of this point number 1. We can get rid of no cloning by using entangled states. And the information is still kind of redundant here, but it's only redundant in one basis. We're spreading it out, but we're not really fully duplicating the quantum part. Now, from the perspective of the rest of these problems, you might start to see an issue here, which is fair. But remember, we're not dealing with the rest of those now. Right now, we're just going to start with problem number 1, and maybe number 2. OK, so in fact, let's think about number 2. So how can we, in this state, how can we possibly correct bit flip errors without destroying the superposition? Right? To make this a really quantum error correcting code, even for just classical errors like the bit flip, we need some way of preserving the superposition. And so the key is to look more closely at what actually happens. So suppose we have a bit flip error on the second qubit, as in the example I had over there. Well, we started with this state, and we ended up with, so an x will take this 0 to a 1, and it will take this 1 to a 0. So we're going to have alpha 0, 1, 0 plus beta 1, 0, 1. So now, obviously, if we measured all three qubits to see what they were, we would collapse the superposition. But notice that these two things share something in common. The middle qubit, in both cases, is different from the first and last qubits. So if we can measure that property, if we can see that the middle one is different, we can in principle, find that out without collapsing the superposition. Okay? So how are we going to do that? Well, so suppose we have this encoding. And we're going to break it down into two steps. Okay? First, I'm going to say, again, looking at these, that so in the original encoding, all three qubits were the same. And in particular, the first and second qubits were the same. But when we have this error, the first and second qubits are different in both terms of superposition. So let's measure that. So how are we going to do that? Well, we're going to take an ancilla, and we're going to do C naughts from the first and second qubits to the ancilla, right? And so if they're both the same, either nothing happens twice or both get flipped, or gets flipped twice. In either case, we end up with 0. But if they're different, one of those is a 0 and one of them is a 1, it'll only get flipped once, and we'll end up with a 1. Okay? So this measurement, well, once we measure this qubit, that'll tell us whether these first two qubits are the same or different in the computational basis. And similarly, we can use an ancilla and two C naughts to measure if the second and third qubits are the same or different in the computational basis. Okay? And so this gives us two classical bits of information about what's going on in the system. And you'll notice that none of this depended on whether we started with a logical 0 or a logical 1. Right? If we had an actual code word, as not having any errors, in both cases, we'll see 0, 0. But in this particular case, where we have an error on the second qubit, both of these will give us 1. Right? Again, whether we had the logical 0 or the logical 1. And so doing this circuit and making these measurements does not collapse the logical superposition between those two basis code words. Okay? So these two bits are called the error synchron. And in fact, by looking at them, you can determine exactly what bit flip error you have in this case. Right? I mean, as I said, if you see 0, 0, that means you had a valid code word, so that's no error. And if you see 1, 1, you know the error is on the second qubit. But suppose you see 1, 0. What does that mean? Well, that tells you that the first two qubits are different, but the second and third qubits are the same. And so that means the error must be on the first qubit, right? That's the one that's out. And similarly, 0, 1 tells you the error is on the third qubit. See, so looking at the synchron allows you to determine what the error is. And then once you know what the error is, you can just do a bit flip to get back to the original state. Okay, so that tells us how we deal with this second problem. Right? By being careful about what we measure, we can measure information that tells us about the errors without telling us about the logical qubit. Okay? So that's going to be our strategy. We're going to add redundant information that lets us make measurements that tell us what the errors are, but doesn't tell us anything about the encoded qubit. Okay? Everyone happy with this? Are there any questions on it? Okay, so then let's start to think about this third problem. We need to correct bit flip errors as well as phase errors. And so in this respect, this code does not do very well. Because, sure, if you have a bit flip error, we can identify where it is and we can correct it. But if you have a phase error, we can't. And in fact, it's even worse than that, because if we just had a single qubit and it has a phase error, then we get alpha 0 minus beta 1. But now we have 3 qubits, and if we get a phase error on any one of them, we get alpha 0, 0, 0 minus beta 1, 1, 1. So before, there was just one qubit that could go wrong. That happens with probability p. Say, suppose you have a dephasing channel with probability p. But with 3 qubits, now it's probability roughly 3p. Okay, so the error rate is higher, in fact, by doing this encoding for phase errors. So we've managed to correct bit flip errors, but we've made the phase errors worse. Okay, so that does seem like an issue. Okay, but let's not try to handle that right now. Instead, let's just do something a little bit easier. So this is a code that corrects bit flip errors. So let's do the same thing, but with a code that corrects phase errors. So bit flip errors and phase errors kind of work the same way. So in particular, let's talk about this plus-minus basis. So most of the time, I'll be dropping this normalization, but for this time, I'll write it down. So plus is 0 plus 1, and minus is 0 minus 1. Okay? And so whereas the original computational basis, the bit flip changed 0 to 1 and 1 to 0, in this basis, the bit flip error takes plus to itself, and minus, well, 0 minus 1 goes to 1 minus 0, which is minus minus. Okay? So in this basis, x acts like z did in the original computational basis. And similarly, z, well, it takes 0 to 0 and 1 to minus 1. So it takes 0 plus 1 to 0 minus 1. It takes plus to minus. And it takes minus to plus. So in this plus-minus basis, kind of the roles of x and z have switched. Right? Z is the one that switches the two basis states, and x does a kind of dephasing in this basis. And so the upshot is that we can do the same encoding, but in the plus-minus basis instead. So suppose we take 0 to plus, 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 and 1 goes to minus, minus, minus. And then alpha 0 plus beta 1 would go to alpha plus, 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 plus beta minus, minus, minus. Okay? So then everything would work the same. It's because we have to do it in this alternate basis, which is related to the original one by Hadamard transform. Okay? So for instance, I didn't write the encoding circuit here, but you could. It would be, suppose we have alpha 0 plus beta 1 on one qubit, and you brought in 2 extra qubits. You can just do 2 C naughts here. And so here I could do the same thing, but I want to do in the Hadamard basis. So let's see. I guess I would do that. Do the same encoding circuit and then do the Hadamards. Okay? And similarly, I can take this thing and then do the Hadamard's back to get to the other basis. So let's start out with Hadamard's here. And then I can do Hadamard's to get back to where I was. And you see what this is doing is it's saying, well, I'm going to just convert the plus minus basis back to 0, 1, and then I'm going to see if they're the same or different in that basis. So this is basically just saying I'm going to see if we have the same or different in this plus minus basis. Okay, and otherwise it all works exactly the same as before. Okay? And so the upshot is that this is a code that corrects a single z error. But of course, just like the previous code corrected x errors and made z errors worse, this one makes x errors worse. Okay? So we have some kind of trade-off in these particular codes of correcting x errors versus correcting z errors. I should have put this one in front. Okay. Well, okay, I guess I have some space here. Okay, so what we really need is a code that's going to correct both bit flip and phase errors in order to address this problem 3, and to do it simultaneously. And to do that, we're going to have to go to more qubits. Okay, so what we're going to do is we're going to do a version of what's called concatenation, which will show up again later in the class. And the idea is we're going to use 9 qubits. So this is sometimes called the Shor code because it was basically the first quantum error correcting code invented by Peter Shor. And the 9-qubit code is this. So this is a notation that I'll be using from time to time. I'll have the bar over inside the ket, over the number inside the ket to indicate that it's an encoded state, a logical 0 state. The logical 0 is going to be the tensor product of 3 copies of 0, 0, 0 plus 1, 1, 1. Hopefully I can fit. Okay, I guess barely. And then the logical 1 is going to be 3 copies of 0, 0, 0 minus 1, 1, 1. And of course, if we have a superposition encoded state, alpha 0 plus beta 1, it's going to be encoded as alpha 0 bar plus beta 1 bar. And so remember, that's how we're not violating the cloning theorem, right? It's certainly possible to have 3 copies of the same particular state. It's just that if we have a superposition of these things, then we're getting some massive entangled state rather than 3 copies of this superposition. Okay? And so this code, I claim, can correct both bit flip errors and phase errors. So it can correct a single x. And how do we do that? Well, we look in each set of 3. And we say within that set of 3, is the first and second qubit the same or different? Are the second and third qubits the same or different? Just using that circuit again. Okay? And it corrects z. Well, that's a little bit more complicated, but it's the same basic idea. We have supposed to have 3 copies of this plus or 3 copies of the minus, or some superposition. But in particular, no matter what, for the valid code words, these 2 phases are the same. Right? And these 2 phases are the same. And so that means that what we should look at is whether these 2 phases are the same or not. If they are the same, that's good. There hasn't been a phase error. If there has been a phase error, then either these 2 phases will be different or these 2 phases will be different. there's only one phase error. Okay? So we're going to correct z errors by comparing phases between the sets. Okay? And so the other thing I want to point out is that this also corrects y errors. And the reason is that a y error up there is both an x and a z error. So it'll show up, the x part of it will be corrected here, and the z part of it will be corrected here. If a y error occurs, what happens is within that set of 3, we'll see, oh, there's been a bit flip error. And we'll correct that like it was a bit flip error. But we'll also see that the phases are different somewhere. And so we'll correct that as well. Okay? So this 9-qubit code then solves our problem 3. It's correcting both phase errors and bit flip errors. So are there any questions on that? Okay, so then let's start to think about this problem number 4. The thing is that, you know, in order to go from correcting just bit flip errors to correcting bit and phase errors, I went from 3 qubits to 9 qubits. And now I want to correct an infinite number of errors, different possible errors. So does that mean I'm going to have to go to infinitely many qubits? That would be bad. It turns out you don't have to do that. But I think this is probably a good time to take a break. So I just wanted to give you some anticipation so you'll come back. And when we come back, we'll discuss how to deal with other kinds of errors using quantum recursion codes. So let's say a 10-minute break. How about that? so maybe we should get started again. So before I do that, were there questions from the first half? Yeah.
So you might have mentioned this and I missed it, but so now you've got 9 qubits, and so you've increased the probability of single qubit errors.
Right.
So is it obvious that the scaling?
Right. No, that's a good question. I did not mention that. Not explicitly. It was kind of implicit in some of the discussion over here. So yeah. Can I write that down? So so in this case, we can just think of it as probabilities of errors. So suppose we have a channel that has some probability of x, y, z errors. So it's some generalized Pauli channel, which I guess is behind. Some Pauli channel. So if we have just one qubit, let's just say it's a depolarizing channel. So x, y, and z are all the same. So we have one qubit, we have a probability p of having some Pauli error. Okay? But now we have 9 qubits. And so the probability of having at least one error is roughly 9 times p. So that's increased. But if there is only one error, one x, y, or z error, we can correct it. So that's not so bad. So we only have a problem when we have 2 Pauli errors. Right? And so what's the probability of 2 Pauli errors? Well, it's this. So it's 9 choose 2, p squared, 1 minus p to the 7th. And when p is small, well, so this 9 choose 2, that's a fairly large number. Right? 36. But p squared, when p is small, is always going to overwhelm it. Right? And in fact, so if you compare this with p, the probability of the error if you had only one qubit, this is going to be smaller whenever 36p 1 minus p to the 7th is less than 1. And for small enough p, that will be true. Okay? So that's the way it works, which is probability of t plus 1 errors is O of p to the t plus 1. And for small enough p, this is always winning, no matter what these constants are. Right? As the constants get bigger, you need a smaller and smaller p to make it worthwhile. But the better scaling is how you win. Okay? I mean, I should say that that's also true even of this 3-qubit code, or this 3-bit classical repetition code. Right? Because you have going from 1 bit to 3 bits, and so the probability of having an error is about 3p. But it's only when you get 2 errors, which happens roughly 3p squared, that you have a problem. But if p is greater than a third, 3p squared is still greater than p. But if p is less than about a third, then it's smaller. Okay? Any other questions? Okay, then let's try to tackle this 4th problem. So again, it looks pretty daunting. How are we going to correct this infinite spectrum of errors? But we have this 9-qubit code. So in the spirit of experimentation, let's look at this 9-qubit code and try to see what happens when we get, say, this continuous phase rotation on it. Okay? We're just going to treat it just the same way as we did before with trying to correct Pauli errors. And I want to see what goes wrong when we have a non-Pauli error. Okay? So to help in the analysis here, let's rewrite this r theta. So it's defined as e to the minus I theta 0, 0, e to the I theta. But we can expand those exponentials. And so we get cosine theta times the identity minus I sine theta times z. Okay? So we're going to expand it in terms of Pauli's, which are things we know how to deal with. And in particular, if we have a state psi in this 9-qubit code, and we do r theta on the ith qubit, then this is going to be cos theta times psi, identity on the ith qubit, we have the psi, minus I sine theta z on the ith qubit applied to psi. Okay? So this is what we have. And like I said, we're just going to do the regular thing here, assuming that there was a Pauli error. And we'll do the error correction procedure as with that. So what we're going to do is we're going to introduce an ancilla. I'm just going to write 0, but it's actually a many-qubit ancilla. We're using it to collect the error synchrome that we're going to measure. But I'm not going to measure yet. I just want to do this step by step. I'm going to do kind of the equivalent of these circuits to figure out where the errors are. So what do? Well, we look to see if within each set of 3, the first 2 qubits are the same or different. Put that in one bit of the ancilla, and so on. The bit flip stuff doesn't really matter. There's no bit flip errors involved here. The phase errors do. So what are we going to get? Well, if we had this state, psi, well, the ancilla would just tell us there's no error, right? Because this state has no error. And if we had this state here, well, that's zi applied to psi. And we know how to correct z errors. The ancilla is going to tell us there's a z error on the ith qubit. So here I'm using some shorthand for what's actually going to be the error synchrome. This is an error synchrome that means there's a z error on the ith qubit. Okay? But then for this state as a whole, well, if this gives this and this gives this, then by linearity, the superposition must give this, cos theta times this, minus I sine theta times this. Okay? I shouldn't say this is equal to this. This goes to that under the synchrome extraction process. Okay? And now the next step is to measure the synchrome. And so what that does is it looks at this register and it just measures it. And these are 2 different values of the synchrome. So when we measure their orthogonal states, we're going to get one or the other. And in particular, with probability cosine squared, we get no error. And with probability sine squared, we get this case where we see the synchrome reports that there's an error zi. And the residual state in this case is this. This, psi. And the residual state in this case is this. Okay? So something kind of amazing has happened. We measured, we collapsed, and the thing that got reported as the error is now the actual error. In this case, there's no error. In this case, there actually is the state psi with an error z on it, on the ith qubit. So it's kind of a testament to the power of wishful thinking. By pretending it was a Pauli error and acting like it was a Pauli error, we made it actually true that the error was a Pauli error. So when I said I wanted to see what went wrong, the answer is nothing goes wrong. It works. We started out with this superposition error, this continuous rotation, and we ended up with either an I or a Z. Okay? And the reason is that this superposition is a quantum superposition between two different types of errors. And by measuring the error, we collapse that superposition. We got one or the other. And notice that this angle has not really disappeared, right? When theta is very small, remember this is supposed to be close to the identity. It's a small error in that sense. And that shows up by saying most of the time when we measure, we get the identity. But occasionally, we get a z. Okay? So these different types of errors two different types of small errors that I was talking about have kind of merged into each other. They started out as a small rotation that always did something, but something not very big, and ended up as a mixture, a small probability of a big error. Yeah?
Why is the channel affecting the ancilla?
Sorry, so this is the error. This is the error. And so what the error does is it takes psi to this state here. Okay, so there's no ancilla yet. So this step here is something that we're doing. So this step here is this circuit, the equivalent of that circuit or this circuit, right, without the measurements. So we're doing an interaction between this code word and the ancilla in order to try to get information about the error. Okay, and then this last step is a measurement that we're doing, again, that we are doing directly on the ancilla. And the reason it can collapse the other register, even though we're not directly measuring them, is because they're entangled.
How do you know you can build how do you know you can actually measure whether or not an error happened in the ancilla? Like, I don't understand how you can write a circuit like that too.
Right. Okay. So yeah. So I didn't tell you the details, but that's based on this property of the 9-qubit code, that it corrects X errors and Z errors. So specifically for X errors, we do it in exactly that way. We're just doing that same circuit in each set of 3. For Z errors, it's a little more complicated because we have to kind of pull out this phase out of 3 qubits. It's not terribly more complicated. Maybe the easiest way I can tell you how to do it is there's a simple circuit that will take. So if you do 2 C0 gates, it'll change the 0, 0, 0 plus or minus 1, 1, 1 into 0 plus or minus 1 tensor 0, 0. Right? You do C0 from here to here and to here. Right? The 1 will make this 1, 1, 1 will become 1, 0, 0. And 0, 0, 0 stays 0, 0, 0. Okay? So we're kind of factoring out, and then it's down to 1 qubit. That's plus or minus, and then we can just do this thing. And then you can undo that to get back to this state. So it's kind of the same way we got to this circuit from that circuit. Yeah?
It's like one way to conceptually think about it, like, so we had some poly error, and then when we went to go measure what error happened, it had to be one of those errors, so the system collapsed one of those errors, we can correct it. And if so, then like what happens if it's not a poly error?
Yeah, so that's the whole point here, is that this is not a poly error that we started with. It started with a thing that's that error up there, r theta. Okay? That's just a small rotation, small phase rotation. Okay, whereas the poly error is a big error. So if you think about the Bloch sphere, you know, a poly error is like 180-degree rotation. And this thing could just be a small rotation. Okay, so that's the whole point here, is that we're starting with something that's not a poly error, but you can still write it as a superposition of poly errors.
And then for all errors?
Yes, yes. I mean, this is going to be important in a minute, but the space of everything that can happen to a qubit, if you look at all possible cross operators, they're all going to be 2-by-2 matrices if you have a qubit in and a qubit out. Okay? And 2-by-2 matrices form a vector space. And the vector space has a basis. It's a 4-dimensional vector space. And what's a good basis? Well, I, X, Y, Z. Those are 4 things. They're all linearly independent. And they form a basis for a space of 2-by-2 matrices. So any 2-by-2 matrix can be written as a superposition of I, X, Y, and Z. Okay. In this particular case, I just looked at it and wrote it down. just kind of expanded it that way. But it's generally true. Are there any other questions? Okay, so then let me continue on that last point. So let's think about the general case, right? As I just said, we can write any 2x2 matrix as a superposition of I, X, Y, and Z. And this argument didn't really depend on the details of this expansion, right? So the same thing should hold true in general. So let me see if I can prove that. Oh, that's out of reach. Okay. Okay, so so in order to prove it, I want to make actually a much more general statement about quantum error correcting codes, not specific to this 9-qubit code. So the first thing I want to do is I want to define a quantum error correcting code. And quantum error correcting code is almost universally abbreviated QECC. Sometimes people just use QEC, quantum error correction. And so we can think of it really, if you want to be totally rigorous, it should be a pair of UE. So U is a unitary encoding map. And actually, it's not unitary. It's really a partial isometry because it's taking a smaller Hilbert space into a bigger Hilbert space. But basically, it's a unitary. I mean, in all practical purposes. And so that's what the U is. And it's going to map a k-dimensional vector space into an n-dimensional vector space. With a set E of correctable errors. And this is not just any pair, it's a pair with the following property, so that there's a decoding map and this decoder has the property that for all errors in this set of correctable errors, and for all logical state psi in the logical Hilbert space, then suppose we take the state psi and we encode it, and then we get the error E, and then we apply the decoder. Okay? So it's an error correcting code. So what we should do is we should get back the state psi. But in fact, there could be some constant of proportionality. And in principle, that constant of proportionality could depend on the error and on the state. But we should always get something that's proportional to the original state. Okay? And the reason we need this constant of proportionality is because we didn't insist that the E's be unitary, right? So they could be messing with the probabilities of things. So, right. And so the other notation here is that we say that a code corrects an error E when it's in this set of correctable errors. So this is the decoder. This is the encoder. And this is the definition of a quantum error correcting code. Okay? Is the intuition behind this definition clear enough? Okay. This one has one too. Let's leave that one up. I need this one. Okay, so given that definition, yeah, okay. So actually, sorry, so a little bit more notation. So, so first of all, I want this to be totally general. So this big K and this big N could be anything, but usually we have big N to be some number of qubits. So it's the dimension of the big Hilbert space. This is the physical Hilbert space. And it involves n qubits, which are the physical qubits. And this is the logical Hilbert space. And again, most often, big K is 2 to the little k. And so there's n physical qubits and k logical qubits. Yeah, and sometimes, of course, I said we're going to be dealing with qubits. And so you might have some other d to the n or d to the k here. OK, so right. So given this definition, we can prove a statement about these kind of superpositions. And it's really quite general. It says that if a quantum error correcting code corrects 2 different errors, E and F, then it also corrects alpha E plus beta F. So I guess I need a little bit of caveat here. So the way I defined it corrects it is you're just given the set of errors script E. But obviously you could write down set E that doesn't contain everything that you can correct. Okay, so this is under the assumption that you're kind of maximizing the possibilities. And so the proof is basically just kind of working on that. So I don't think I'm going to go through the details. It's basically the same idea, but you have to be a little more general. And the upshot is that, so for instance, for the 9-qubit code, as I said, X, Y, and Z form a basis for the space of 2 by 2 matrices. So that means we can correct any 2 by 2 matrix. And more generally, if you have a t-qubit error, well, t-qubit errors are 2 to the t by 2 to the t qubit matrices. Well, if you restrict to t particular qubits. And those can be, and the basis for the space of 2 to the t by 2 to the t matrices is tensor products of I, X, Y, and Z. So, so a quantum error correcting code that corrects weight T tensor products, by which I mean all weight T tensor products of the polys with the identity, therefore corrects any T-qubit error. So why is that? Well, what's a T-qubit error? It's Krauss operators can all be written as superpositions of weight T things. And any weight T thing, and a superposition of weight T things, any weight T thing can be written as a superposition, as a sum of these polys. So if we correct these polys, we correct any weight T tensor product. And then we can correct any superposition of different weight T tensor products, even if they're acting on different qubits, again by this theorem. And therefore, we can correct every Krauss operator. And so we can correct, kind of the arbitrary error there in the CP map. Okay? And the particular application to what we've done so far is that we don't actually need to do anything extra to handle continuous rotations, decohering maps, etc. Right? The 9-qubit code corrected arbitrary 1-qubit poly errors, and therefore corrects arbitrary single-qubit errors. So it really is a true quantum error correcting code, correcting anything that can happen to a single qubit. Okay? So are there any questions on that? So I'm about to switch topics a little bit. Okay, so in that case, let's continue this idea of saying general things about quantum error correcting codes, and try to think about, for general quantum error correcting code, if you want to correct some set of errors E, what do you have to do, right? How can you tell if you've done it, and how can hopefully you design codes that do it? So what properties does that error correcting code have to have? Okay, so thinking back to the way we analyzed the 9-qubit code, we said, okay, we have a bunch of different errors, and we're going to identify them by interacting with some ancilla qubits and then making a measurement. Okay, and in order to say distinguish a bit flip error on the first qubit from a bit flip error on the second qubit, well, they had to be orthogonal states to begin with. And if they are orthogonal states, then there's some measurement we can do that will distinguish them. Okay, so that's kind of the idea that we're going to work with. So what we're going to say is, suppose that we have some set of possible code words psi, and we have some set of possible errors, which just for notational convenience, I'm going to say are EB. Okay, so these are kind of the set of things that we have to deal with, set of possible states that we're going to get after the errors occurred. And what we'd like to say is that it would be sufficient if everything that had the error EB on it was orthogonal from anything that had the error EA on it. Right? Then we could make some measurement that would distinguish. There would be some subspace of things that had error EA and some subspace of things that had error EB, and they'd be orthogonal to each other. So we could make some measurement that would distinguish between these two things. So that's saying that phi EA is orthogonal to EB, sorry, EA phi is orthogonal to EB psi. So this should be 0 when A is not equal to B. When A is equal to B, it can be something else. So for instance, it would be sufficient if it were proportional to delta AB. Okay? Then it would be all the same. And so what should that constant of proportionality be? Well, okay, yeah, we don't really need that. Okay, no, yeah, sorry. There's something I want to say. So, okay, so this is for arbitrary states psi and phi. Okay, so so in the case, again, think about the 9-qubit code. In the case where EA and EB are Pauli errors, well, when A is not equal to B, this is telling us we get 0. When A is equal to B, it's like x dagger x. And if you look at x dagger x is just the identity. In fact, all of these are unitaries, so that's always going to be true. And so in the case where A is equal to B, these cancel and we just get this inner product, psi phi. So, so this would be sufficient, at least for Paulis. Okay, and this psi phi really does have to be there because you know, if these are the same state, well then, and we get the same error, then obviously we're gonna have inner product 1, right? But if these are orthogonal states, then it's actually important even when we have the same error. So if we have EA here and EA here, it's important that we don't mix up, say, the logical 0 with the logical 1. Right? So those things should remain orthogonal. Because our decoder can never make them more distinguishable. Right? So if they lose distinguishability, then we're out of luck. We're not going to be able to correct. So it's definitely the case. And the error is not going to, well, the error is non-unitary, so it could, in principle, make them more distinguishable. But it's not going to in the cases where we can correct. So we actually always do need this inner product here. When psi and phi are close together, they remain close together. When they're far apart, they remain far apart. When A is equal to B. Okay? But this is sufficient, but it's definitely not necessary. So for instance, if we had Paulis, but we just scaled them down, right? Like we have, you know, instead of x, we have x over 2. Then for say one particular value here of A, then this would no longer be true. So what we can do is but that wouldn't really matter anything, right? That's just affecting the probability of getting the error x, not affecting our ability to correct it. And back in this definition over here of a quantum error correcting code, we kind of built that in to having this constant factor here. And so what we can do is it's really sufficient to have some other thing here. So this is just some diagonal matrix. Okay? And once we have this actually is sufficient to correct the errors, right? Because we say, oh, different errors are orthogonal subspaces. So we can make some measurement that will distinguish those. And within each of those subspaces, we're kind of replicating the inner product structure of the original logical Hilbert space. And therefore, there's some map we can do that will take that Hilbert space back to the original one. Okay? The argument is made more carefully in the book. And so this is now sufficient with this modification. It's sufficient for all errors, for all sets of errors. Okay? So if this is true, then this error correcting code can correct, if this is true for all pairs A and B in this set E, then this error correcting code can correct that set E. Okay? But suppose, well, okay, but we also want to know what a necessary condition is. Okay? So to understand that, let's take advantage of this theorem. So we have some basis of errors that we're using here. And that gives us these orthogonal things. But this theorem says we could equally, instead of picking that basis of errors, we could take any linear superposition of errors. So, I mean, this theorem says that we might as well let this curly E be a vector space of errors. We can take the linear span of anything we have in it. And we can choose a different basis to work as our main set EA and EB. Okay? And suppose we did that. Suppose we write down some alternative basis. Well, then we can write it in terms of the original basis, like so. Okay? And then let's plug that into these conditions. So let's look at let's look at an inner product phi FA dagger FB psi. Well, plugging this in, we get sum over C and D, alpha AC star, alpha BD, and then phi EC dagger ED psi. And this, we're going to plug in this condition. And so when we do that, the terms with C not equal to D drop out. And so we get sum over D, alpha star AD, alpha BD, CD, and then phi psi. And then we can take this thing and rewrite it as a different constant. That depends on A and B. And this gives us kind of a different version of this condition for a different basis. Okay? And so, in fact, that turns out to be both a sufficient and a necessary condition. So a subspace Q is a QECC for the set of errors E. If this condition is true for all code words in the code and all pairs of errors. Okay? For some, so the thing that's important is to note that this coefficients here, CAB, don't depend on phi and psi. Okay, so that's what makes this non-trivial. Yeah.
I'm guessing we also want this CAB matrix to be invertible.
Well, so no, it doesn't have to be invertible. It does have to be diagonalizable, but that's not a condition that happens automatically. Why? Because suppose you take the complex conjugate over here. Well, that switches this. We get psi EB dagger EA. And on this side, we get psi phi, and we get C AB star. So that's saying that this is Hermitian, right? Because when we switch this, sorry, when you switch this, when you take the complex conjugate on this side, we're switching the psi and phi, but we're also switching A and B, right? So we're getting CBA. And then, but on this side, we just get CAB star. So that's saying that CAB is Hermitian, which means it's diagonalizable. But it doesn't have to be invertible.
So what if they were all 0?
Yeah, well, they can't all be 0. Well, they can all be 0. What that means is that the probability of having these errors is 0. I'll get to this in a second, actually. Well, a few minutes anyway. But basically, it's acceptable to have 0 eigenvalues. And basically, that boils down, like I said, to those errors having 0 probability of actually happening. Yeah.
So in the definition of a QECC, it's a pair of encoding map.
Yeah.
So,
And here I said it was a subspace.
so
Right. Yeah. So what I've done is I've kind of scoured away information that didn't matter. So the subspace here is the image of that U, that encoder U. And of course, there's different encoders U that will correspond to the same subspace Q. But they don't affect this condition, right? Because this didn't care about exactly what logical things psi and phi corresponded to, right? It just cared that they were code words. And so frequently when we talk about quantum error correcting codes, again, we're interested in the error correction properties. We don't really care exactly where the logical qubits get mapped. So if you want to be really strictly formal and capture everything about the quantum error correcting code, you should include it, define it that way and include the encoder map that says how the things. But frequently people don't bother to do that, and they just talk about the subspace. So that's what I've done here. Yeah, so sometimes, I would say most of the time when people say a quantum error correcting code, they're actually just talking about the subspace. Any other questions? Okay. Let's see. So before I get to this thing about zero eigenvalues, there is some alternate versions of this thing that are maybe a little more common. So for subspace Q and errors E, the following are equivalent. So one is the version that I've just said. So let me actually make these errors E should be a linear space. And actually, in this condition, I didn't really insist that it be true for all errors, pairs of errors in a linear space. It was sufficient and necessary that it be true for a basis of errors. That was what my argument showed. So the other thing I can do is, but I did demand for all pairs of states in Q. So the other thing I can do is I can restrict attention just to a basis in Q. Oh, yeah.
And so you said Q is the image under the encoding map. Is that the image of all the states in the logical Hilbert space?
Yeah.
Or can you have a subset and still define this?
Well, if you had a subset, then it would just be a smaller quantum error correcting code. But you'd think of it as a different code then. So the other thing I can do is I can just look at the basis for the code space. And so then I would write something like this. So you see the difference here is I'm just restricting to a basis, and because then, so this is clearly including this, right? This one is clearly stronger than this, right? Because I'm just restricting to a basis. But this one actually implies this as well. Maybe not quite as obvious, but it's easy to show. So another equivalent version is to, instead of varying over different states here, and this is a little less obvious, is to just pick one state. So again, this is a special case of this, but it's maybe a bit more surprising that this actually implies this. And this has to be true not just for basis, but for all states in Q. And then another thing you can do is you can make the errors the same as well. And of course, there's other variations where you have E dagger E here, but psi I, psi j, for instance, or phi psi. That's fine. So these are, you can kind of separately manipulate the states between basis and the same, different, whatever, and the errors. Okay? So these are just all different versions of the quantum error correction condition. And in some cases, one of them was more useful than others. Okay. And then another definition. So frequently when we talk about error correcting codes, we are interested in the specific case where E is things of weight T or less, or weight T errors, right? It's the span of things of weight T. And so in that case, we want a code that will correct arbitrary T-qubit errors. And so kind of applying this theorem, we see that the thing to look at is the following quantity. But okay, let's see. So let Q be a subspace of an n-qubit Hilbert space. So for this definition to make sense, I'm going to need to be breaking the big N Hilbert space down into smaller components, usually qubits. And then we say the distance of Q is the minimum weight D of a tensor product error f such that, what's the quantity that shows up here? It's things of the form psi f psi. So in this case, f is combining EA and EB. Or you can think of it as EA dagger EB. And these quantum error correction conditions fail, and for instance, the last one fails when this thing here is not purely a function of f. If it also depends on psi, then this is not true. And the error correction conditions fail. And if the dimension of Q is big K, then we say this is an little n, big K, little d code. So G is the distance, talking about the smallest weight operator that causes this QECC condition to fail, basically. N is the number of physical qubits. K is the dimension, not the number of qubits, but the dimension of the logical subspace. Okay, and then these double parentheses indicate that it's a quantum error correcting code. Yeah.
So does this F has to arise as like product of errors, or?
So the way I've defined it, F has to be a tensor product, which means that it will in fact be a product of two smaller things. But for the definition, F should just run over all tensor products. Okay, so this definition of distance is focused, again, on the case where we want to correct all errors up to a given size. And what that means is that if you have all, suppose you want to correct, I want to put this in, but I don't quite have enough space. So suppose you want to correct t-qubit errors. Well, for instance, I can run over all t-qubit Pauli errors for EA and EB. But then the product, EA dagger EB, could be some arbitrary 2t qubit Pauli error. Right? And so if psi f psi is equal to C of f for anything of up to weight 2t, then the quantum error correction conditions hold and we can correct t-qubit errors. Right? So that means that we want a code that has distance at least 2t plus 1. Okay? So if we have a code, for instance, of distance 3, that means, well, there's some 3-qubit product here that causes this to fail. But for any 2-qubit product, which is what we could get by a pair of 1-qubit errors multiplied together, it'll work. And so with a distance 3 code, we can correct 1 error. If we want to correct 2 errors, we need a distance 5 code. Okay? And so conversely, if you have a distance d code, you can correct floor of d minus 1 over 2 errors. Okay? So any other questions about that? Okay, so So you might ask, what's kind of the point of having a definition like this? In order to correct t errors, you need a code of distance 2t plus 1, which is always going to be odd. But this definition makes perfect sense even for even distance codes, right? Like 2 or 4 or 6. But who cares, right? If you have a code of distance 4, you can still only correct 1 error. It's not enough to correct 2 errors. But it turns out the distance also captures other properties of the code. So in particular, it captures the ability to correct a different kind of error. That shows up a lot. So an erasure error is an error on a known set of qubits. Okay, so for instance, if you have 5 qubits and you send them through some quantum channel and the first one just doesn't arrive, that would be an example of an erasure error, right? It's been erased. So in that case, you know that the first qubit is wrong because you don't have it. You could put something else in its place, but it would just be a random thing that you're replacing it with. But if that's the only thing that can go wrong in this channel is the loss of qubits, then we know if we get all the qubits that they're all right, and if we get 4 out of 5 qubits, then all those 4 are right, and it's only the one that's missing that we have to worry about. And so that's an advantage, right? Because we have some information about the error. We don't know exactly what happened to the qubit, right? It's been taken away and replaced with something random, but we know where the error is. And so that actually makes it easier to correct errors. So if you look at these quantum error correction conditions, you might say, OK, so we have EA, dagger, EB, but the set of possible errors is only errors on the missing qubits. So what that means is that EA, dagger, EB is going to be limited because if EA is affecting at most t qubits and EB is affecting the same t qubits, then EA, dagger, EB is still at most t, right? This is the weight. The number of qubits that have been erased. Okay? And so suppose we have now a distance d code where d could be even. And we have an erasure channel that has erasure errors. Well, if t qubits get erased and we have a code that's distance t plus 1, that means that the only things we can get in this product are things of weight t, and so we're OK. Yeah?
Can we fix erasure errors using kind of the theorem that was just a poly?
Yeah, sure. So again, if you restrict attention to these t particular qubits that have been erased, well, it's a 2 to the t by 2 to the t matrix on those qubits, which again can be written as a sum of tensor products of polys on those qubits.
But if it's like a 0, 0, 0, 0 matrix, how do you your linear?
Sorry, this?
Yeah. Is that
Well, this is a superposition of 0 polys, right? It's 0 times identity plus 0 times x plus 0 times y plus 0 times z. So that's fine. And that one is OK because it doesn't happen, right? The probability of this thing is 0.
But I thought we can assume there's non-unitary errors.
Yeah, sure. So, but that's interesting for stuff like this.
Okay.
OK? And so this is an interesting error. But this is it's a half I plus Z. You see 1, 1, and 1 minus 1. Okay? Okay. So anyway, so the upshot is a distance D code can correct D minus 1 erasure errors. So I should say that the tricky thing about this is that the erasure errors, once Bob receives it, he knows which qubits have been erased. But when Alice sends, she doesn't know which ones are going to be erased. Right? If you knew which ones are going to be erased, it would be very easy, right? Because you just say, I'm not going to use those. I'll just encode it on the other qubits. But if you don't know, then it's more complicated. You have to spread the information out because you never know if the particular qubit that you're relying on is going to disappear. Okay. And the other nice thing about erasure errors is that it allows yet another alternative version of the quantum error correction conditions that's really, really quite nice and has a lot of independent kind of applications. So we can say a quantum error correcting code corrects for erasures on a set S of qubits if and only if trace over S complement of the code words. So this is going to be a subspace again. Q is independent of psi in Q. Okay? So what does this mean? Well, okay, first, how do you show it? So, so going back to, I guess, this condition, we can say, well, so we're correcting erasures. And these things can then run over arbitrary pairs of operators on the erased set S. Right? And this thing over here doesn't depend on the state psi. So if you look at what I've written here, trace of SC psi psi, well, that's okay, so this is going to be independent of psi if and only if so what this is saying is that the density matrix on S doesn't depend on the state psi. And what this is saying is you can do whatever you want on the set S, and it's not going to affect this inner product. And yeah, sorry, I'm not thinking clearly about how to make this obvious. But so you suppose you take this density matrix, right? So this thing here will only depend on this density matrix, this inner product here, right? Because E is acting on rho. And so the stuff that's kind of outside rho, you can just pretty much ignore. It all cancels out. And it's only the stuff on rho. So for instance, you could let E here be a projector on some particular value in the set S. And Yeah, okay, I better not try to reproduce the details of this argument right now. So I think it's almost certainly in the book. So if you're interested in the details of how to show this, it's there. But intuitively, this is actually maybe not that hard to see. So again, this is the density matrix on S that we have here. We're saying it's independent of the state psi. And this here is saying that whatever we do on the set S gives us some inner product that doesn't depend on the state psi. And the upshot is that this condition is saying that you can correct for a set of erasures if and only if the density matrix on those qubits has no information about the code, about the logical state. Now, that makes sense in one direction, right? That if it had information, then you shouldn't be able to correct for losing that. Because somebody could take those qubits and learn some information about the state, and that would be destroying the superposition in the encoded state. So what's maybe surprising is that this is if and only if. So it's not just a necessary condition, but it's also a sufficient condition. That if you can exclude information from certain subsets, then you can correct for erasures on those subsets. Okay. Okay, and so the other thing about distance is that it's also good for detecting errors. So I don't want to go into details about that, but distance decode can also detect up to d-1 errors. So you don't know, in this case, you don't know what qubit they're occurring on. It's not erasures. And you're not trying to identify exactly which errors occurred. You just want to know that there's been an error, that it's not the original state. Okay, but the last thing I do want to do is to get back to this question that we had about the 0 eigenvalues for this matrix CAB. Do I still have a 9-qubit code under here? I do. Okay, that'll be convenient. So so we say a quantum error correcting code is degenerate if CAB is not full rank when the set EA are linearly independent errors. Running out of chalk here. Okay. Okay. So this is explicitly allowing those 0 eigenvalues, and if it is full rank, then the code is non-degenerate. And so this is something that actually is unique to quantum error correcting codes. It's something that doesn't really happen in classical error correcting codes. And what this is saying, if you look at these conditions, is that even though the errors are linearly independent, they do linearly dependent things on the code words, right? Because this matrix was derived from the inner product of EB psi j with EA psi I. Okay? And in particular, the easy case you can see when you get a degenerate code is you have two errors that are distinct errors that do the same thing to different code words. Right? So, sorry, not same thing to different code words, same thing to the same code word. So for instance, if E psi is equal to F psi, then that implies that E minus F psi is 0. And that's when you can get a 0 eigenvalue here. And so, like I said, classically, this doesn't really happen. I mean, you can kind of mock it up, but not in this kind of standard models of things. Additive error, it's called. But quantumly, it does, and it's actually pretty common and important. And in fact, I've already shown you a degenerate code. This 9-qubit code here is a degenerate code. Why? Well, suppose you have a z error on the first qubit. What do you get? Well, this one would go 0, 0, 0, minus 1, 1, 1, then plus, plus. This one would go 0, 0, 0, plus 1, 1, 1, minus, minus. But suppose you have a z error on the second qubit. You get the same thing, right? So z error, z1 is equivalent to z2 on this code. They're degenerate errors. Okay? And the existence of these degenerate codes actually makes the theory of quantum error correction in a number of ways more difficult and more complicated than the theory of classical error correction. And so something that, yeah, it probably won't show up too much in this class because the things where it shows up are maybe more advanced and therefore beyond the scope. Another way to think of it is that if it weren't true, then I could include those things in the class. But because it is true, it does happen, then it's kind of hard to handle those cases. And in some cases, they're still subject to very active research. So that's the last thing I wanted to do today. Before we get people leaving and stuff like that, if there's anyone that did not get a textbook, I still have some copies here and also the problem set due next Thursday. I guess you can turn it in class next week. I still have to work out with the TA how we're going to handle that. But for next week, at least, turn it in to me here, and we'll sort it out. Oh, yeah. So questions?
So for the degenerate codes, so if we know that the CAB is not full rank, then can we conclude that there exists two errors such that they act on the same?
I don't think that has to be the case. So, I mean, I don't know of specific examples, but in principle, you could, for instance, have 3 errors where no 2 of them are the same, but this was true. Right? I mean, in some sense, I guess you could say, well, then one of the error, you could let one error be EA and the other EB plus EC, in which case it would be true. But these could, even act on different qubits, different sets of qubits. So it could be fairly complicated. Yeah.
If you have some degenerate code for a set of errors, is it always going to be a degenerate code to correct those errors, or is there some sort of non-degenerate code that you can find some other way?
So this type of argument shows you that if you change the basis for the set E, then you're kind of doing a standard basis change type thing on this matrix CAB, and so therefore full rank, not full rank. That's something that's preserved under those things. This is a GLN transformation, so it's an invertible transformation, not a unitary one. But invertibility still is preserved. Now, obviously, if you were to say restrict your set of errors to make it smaller, then that might not be true anymore. Any other questions? Okay. See you next week.